All right, so this is chapter 9 on ice and glaciers and wind and deserts. And we're going to be starting with glaciers. So, a glacier is a massive ice that moves or flows over the land under its own weight. In order for that to happen, the climate must be cold enough that the snow doesn't melt in the summer. Um, Glaciers, so because of that, they're usually in really high elevations where it's colder up in that alpine level, or in the poles. Um, yeah. So for glaciers to form, you have to have enough precipitation, um, and you can't melt over the summer, so it needs to accumulate, and it usually starts accumulating on slopes that are protected from sunlight. Snow transforms to ice. Over time, the overlying ice will pack the ice tighter and thicker. Packing causes the ice to recrystallize into a denser ice called firn, which is an intermediate texture between snow and ice. So the ice in glaciers are actually it's a rock. We consider them a rock. There are two types of glaciers. There's the alpine and the continental. The alpine are what you find up at the tops of the mountains, and continental are what you see at the poles. Cover large continental areas. Like when you think ice age, you're thinking continental. When you're thinking mountains, you're thinking alpine. So glaciers flow downhill just like water does. You don't really think of a solid as flowing, but it's the weight. So if you think of, it's snowing here where it's accumulating and that gets really, really heavy, which pushes things downhill a little bit. So it's the weight of where it's accumulating that's pushing it down and it flows very plastically. So it's not like a fluid, it's like well, like you would find the, depths of the earth kind of motion in the mantle. Um, and so it's slow. It comes into contact with the valley floor and sides, which slows it down. So if you look at these vectors here, uh, on the sides and on the bottom, the vectors are much smaller, meaning it's flowing much more slowly than in the middle. Um, except for sometimes you'll get streams like in the bottom. That's a different story. Can surge. Alpine glaciers can move fast for short amounts of time, like maybe during the winter, a whole lot of accumulation and push it down, but it doesn't continue. Um, so here's some terms. So the equilibrium line is the point, this like location on the glacier where the material lost, called ablation, and the new snow added, called accumulation, equals each other. And so that is just the line on the glacier. Um, so if you're overall losing material and your equilibrium line is moving up, then you are receding. And you see that when the edge of the leading edge of the glacier moves back. Here is the trend. We are definitely getting out of the last ice age. So this is showing the annual amount of ice loss, which seems kind of steady. But then when you add that all up, the red is cumulative. So you can see since 1980, which really wasn't terribly long ago, we've lost a lot of ice. What is this? In meters of water. Must be cubic meters. Um, Glacial erosion. So as the ice is being pushed downhill, it is picking up little pieces of rock. If you think of like when you've made a snowball, like a snowman, and you start like rolling that snow on the ground to get a bigger and bigger snowball, it's picking up all those little pieces of whatever, little pieces of dead grass or little pieces of gravel, right? And like kind of gets incorporated into that snowball. So the same thing happens here, but like on a much larger, grander scale with a lot more force, where it's not just really little itty bitty pieces like your snowman snowball is picking up. It is like flattening huge areas like the Great Lakes were carved out from the continental glaciers. Mountaintops are carved out. Huge rocks, huge pieces are plucked up and moved or and kind of flattened out. So like you're plucking, I just said that small bits of rock are torn away as ice flows over the frozen water. And it's, frozen water seeps into the cracks and then it refreezes, which breaks up the rock even more and makes it loose. And then it gets plucked away and then it just continues, right? Abrasions are erosion by wind transported sediment or by the scraping of rock fragments frozen in glacial ice. So just when you see it kind of being scratched, although when I think scratching, I usually think striations. Here is a picture of striations, which are parallel grooves and they show the direction that the ice flowed. So if you see this rock, if you're in like a glacial valley and you find bedrock and it has all these little scratches in it, you know that the glacier was moving in this direction. Here are some erosion vocab words. We have a cirque. This is alpine glacial glaciers. This is where it's carved out the mountaintop. So it started on that kind of shadowy, not sunlit slope of the mountaintop. And as it accumulates, it comes down and it carves out this bowl at the top. And we call that a cirque. Now, where it's coming down to, it forms this valley. Now, this probably was like a natural low point at some point in time, a creek or something, just a low point in the mountain range. So it's going to follow that downhill, but it carves out these U-shaped valleys, which are very broad and not narrow. The river-shaped valleys are kind of V-shaped and pointed at the bottom where the river is. This doesn't have that single point. It's this massive thing. So they're more U-shaped valleys. Um, and then sometimes these kind of intersect. Like if this was coming this way and then there was another big glacier moving this way, where they kind of like how a river tributary meets into the main channel, same thing. And so this other one can be deeper. And so you'll have this other glacial valley here and it's deeper where this one flows into it. So it's higher up in elevation. And then it meets this cliff right here. So then it's just like this valley. And then there's just this cliff into this other valley. That is, if you've ever been to or seen pictures of Yosemite, that's what causes all those waterfalls in Yosemite on those cliffs, is there. Now there's water just flowing in these valleys. And then when the one glacier intersected with the other, you get those very drastic, sharp drops with the waterfalls that are so pretty. A red is this little peak here between two cirques where this has been eroded, this has been eroded, and this is what's left. And a horn is pretty much the same concept, but where it's been eroded on all three sides. So if in this picture, if on the back of that was another cirque and you had this one original peak, that's a horn. Now we're switching from erosion to deposition. So glacial deposits are very unstratified and unsorted. They are just this random pile of junk. Most other depositional processes leave things stratified by grain size, usually coarser on the bottom, finer on top if your energy is decreasing. Maybe reverse that if your energy is increasing with deposition. Um, we've talked about how rivers and wave action will sort material. So you get, most of the deposit is kind of the same size. It's all sand or it's all gravel, maybe that remains. This is everything from clay to huge, huge boulders just dumped in a pile. And that is, we call that till. And it's kind of a catch-all term for anything from a glacier. And it can be over very large areas as well. Outwash is what's deposited from streams as the glacier is melting. And that doesn't necessarily mean like at the end of the ice age, but there does come a point where the glacier comes so far south, it's going to melt and you have the stream coming off of it. And then all the sediments that it's picked up at the point where it starts melting, it'll wash some of that down as well. Moraines are where all this sediment that has been well, not necessarily collected, but pushed downward by this flowing glacier. These are moraines. And so this is an end moraine here. Um, there are also terminal moraines where the same thing happens on the side. And so you get these piles of till in front of and on the side. Um, or did I say terminal? Sorry, that's not the right. Terminal is the furthest one. I think I might have read that if I said terminal, but you'll get them on the sides, these moraines, and then you'll get the in moraine, and then the terminal moraine is the furthest moraine that you find out. And so, if you're looking at historic glaciers and how big they used to be, you'll find these moraines, find one here, and then it'll kind of bump over that, you'll find another one. And then there comes a point you come so far south, you don't find them anymore. And so then you can say, okay, well, this moraine here was the largest that the glacier was before it started melting. Ice ages. Few things that cause ice ages. This is going to talk about insolation, which is the amount of solar energy that reaches Earth's surface, and Milankovitch cycles, which are all sorts of things in space. We have the Earth's axis is not north-south, it's tilted and it wobbles around that tilt. So depending on how the tilt is, the degree of tilting, the sunlight is going to hit different parts or hit the globe in different parts. And so that changes through time, as well as the orbit changes. It goes from more elliptical to more circular. And so here you can imagine if it's more elliptical, you are further away from the sun at these seasons here than you are in a circular orbit. Um, let's see. Orientation in space, the shape, yeah. So as all of these things change, in like a solar system level, that affects how much solar energy is reaching Earth's surface. So the energy, this comes down to the tilt. So if it's at a high tilt, we're getting lower angles than if it were like straight on, kind of the difference between summer and winter. Um, so in the winter, we still obviously have daylight, but it's hitting the southern hemisphere more directly than it is hitting the northern hemisphere. And we just kind of get that low angle, which doesn't have as much energy in it. And then we will move on to wind. Oh, wait, let me just go back if it wasn't clear. As these things change, then in the past, then we have had ice ages and not ice ages, apart from like our atmospheric composition.